If you are roughly from the same generation as I am, you are probably familiar with the game Temple Run. Back in the days when smartphones were still this new cool type of phone, Temple Run was one of the most successful apps out there. If you're not familiar with the game, I can basically explain it in one sentence. Survive as long as possible by not crushing into any obstacles, falling down a cliff, or getting eaten by this giant monster that follows you. What you're currently watching is not me playing, but an AI that I trained. Of course, you might ask yourself now, Marty, why build such a completely unnecessary program? And the answer is actually very simple: to beat and humiliate my roommate Nick. Let's start by talking about the general idea behind this program. What we are going to do is use a learning technique called supervised learning. What this means in practice is I will record myself actually playing the game. These recordings I will then use to train a machine learning model. This learning technique is called supervised learning because the model doesn't learn on its own, but it relies on data which I provide to the model by playing myself. This basically means the model learns to copy my own playing style, instead of figuring out the rules and strategies of the game on its own. Now at this point some of you might be like, wait a second. If this model only learns from your own playing style, then it can never play on a higher level than yourself. To which I can only say, not necessarily. That is because for the training process, I will simply not use data from situations where I made mistakes when I was playing. Intellectually, I always know what to do in each of those game situations. That means I can also teach it to my model. If I ever die in this game, this is mainly because of two reasons. Either a lag in reaction time or in concentration. Since our program can be superior in both of these, it can hopefully also play better than us. Alright, enough theory, let's implement this actually in practice. We start with a very simple function which simply records our screen. So if we execute this and we have our game open, then we see basically a copy of our screen. However, simply recording what can be seen in the game is not quite enough because we also need to detect which actions we take in the game. Remember, in supervised learning, we want to teach the program in which situation it is supposed to press which button. Right now it can detect the situation, but not the action. So we need a second function which detects which actions we take. This function looks like this, and all it does is detect which keys I press on my keyboard and assign a number to them. Alright, so let's put this function to the test as well. The image and action detection here works pretty fast, so it's hard to see if everything works fine. So let me just work in some slow-mos here. But of course I tested all that a bit more extensively, and you can definitely trust me that everything works fine. In order for us to gather training data, there's actually only one last thing missing. What you see here is our endless loop where we detect our image, output that image, and detect our action. Our current problem is that our program can now detect the images and actions, but it cannot store them. Which means we will create a CSV file, which we will just call database1. And in this CSV file, we will simply store our data, which is nothing but our image combined with the action. Now let's see if this works the way we want it to. Up here we have our database1 file, and if we click on it, we see that it's completely empty. But as we execute our program and start a game, well, first of all, we see that up here it's getting very laggy. And if we stop our program now, and we take a look at the database1 file, we can see that it's definitely not empty anymore, but actually it's filled with 300 megabytes of data. This certainly explains the lag in the video output. If only a few seconds of gameplay lead to 300 megabytes of data, you can imagine how much data we need if we want to train a model with several hours of gameplay. The main problem was that we extracted too much data. But in our use case, this much data is not only unnecessary, but can even be detrimental. So in order to solve this problem, we will simplify our image detection. First, we will convert our image to grayscale, which should already decrease the size of it by a lot. Typically, a colored pixel is defined by 3 numbers for the amount of red, green, and blue in it, while in grayscale images, pixels are defined by only 1 number. Another thing we should do is resize our image. Right now our image is unnecessarily large, so let's just try decreasing it to 20% of the original size. Now let's check real quick if this managed to solve our problem with the lag. Up here we have our database1 file again, which is empty. And if we execute our program for a few seconds, so the lag has definitely disappeared. Now let's see what happened to our CSV file. And as expected, it shrank from 300 to 20 megabytes. This is because the file doesn't save the data of our original images, but of our simplified ones. Now at this point there's still a lot left for us to improve, but at this point I just want to play for a few minutes and train a model with it. Of course this model will not perform very well, but it is mostly about seeing if the code works theoretically. So let's play a little test game and see you back in a minute. Since not every person will exactly know what a neural network is, and it's important to me that also beginners have an understanding of what's happening here, let me try to explain the absolute basics of neural nets in under 60 seconds. Artificial neural nets are typically built up in 3 layers: an input layer, a hidden layer, and an output layer. While input and output layers are usually one-dimensional, the hidden layer often consists of several layers. Each layer consists of so-called neurons. Neurons are basically placeholders for values that are given to them. The different layers and neurons are connected to each other via so-called weights. While transferring the values from one layer to another and one neuron to another, the weights also manipulate these values. In our example, the input is each pixel of our image, and the output is what our program thinks will be the correct move. An untrained model manipulates these values in a super random way and will therefore also deliver random outputs. But as we train our model, the neural net starts to understand how it is supposed to manipulate the values that are given to it, so that eventually it delivers accurate outputs. What we will do now is take the data from this short game that I just played and feed this data to a neural net. Now of course one game will not nearly be enough for the model to learn anything. But right now I just want to see that the code works in general. What we already know is that our model will need 9625 input neurons, because that's how many pixels our recorded images have. And 7 output neurons for the 6 possible actions, plus the option to do nothing. What we don't know right now is what a good hidden layer might look like. So we start with some arbitrary architecture and worry about that later. Alright, let's start the training process. Alright, and then we can already take this model and probably watch it fail miserably. This little piece of code is already all we need to let our model play for us. We get our image data, then we use that data to predict the next action, and finally execute that prediction. Now there are 2 more lines which I added, and this is a timer where we take the start and end time for each prediction. This is which we are going to be interested in now, because it'll be helpful to know how long our model needs in order to act. So let's test it right away. As expected, our model performs as bad as it gets. The interesting part is that we now know our model makes roughly 30 to 25 decisions per second. Since Temple Run works at 60 frames per second, this means we have roughly a 2-frame delay between seeing a picture and acting on it. This is of course not much, but since we are striving for perfection here and there is an easy fix, we should improve that. The fix actually involves only 2 simple steps. First, we make sure that we gather our training data at the same frequency as our model works, and then we shift our database so that our images are paired with future actions. This way we train a model that doesn't predict what it should have done 2 frames ago, but instead what it is going to do in the next frame. So I just finished this last feature in our code. So what's going to happen now is that we will play for, let's say, 30 minutes, then look how our model performs and go from there. After those first 30 minutes of gameplay, I trained our neural net, and I was actually quite confident that it'll get past the first few obstacles. To my surprise, however, when I tested the model, this is what happened. This was especially surprising to me because at the end of the training process, when the model gets tested on some validation data, it showed a 85% accuracy. This basically means the model is capable of pairing 85% of game situations with the correct action. This should have been easily enough to master at least the first jump, but apparently it wasn't. So what did go wrong here? Eventually I found the problem by taking a closer look into our database. If we analyze the training data, we will see that roughly 90% of the time the action was to actually do nothing. This means during the training process our model learns that it just predicts to do nothing every single time it gets an accuracy of 90%. To solve this, I simply extracted only the frames that were connected to taking no action and deleted a good chunk of them in a randomized way. Thereby I managed to increase the percentage of actions in the training data from roughly 10% to about 40%. If we only look at the number of our validation process, at first it may seem that this change was detrimental. Before, our accuracy was 85%. Now it's only 72%. But as I just explained, it's really hard to compare these numbers, since on this new dataset it is much harder to achieve high numbers of accuracy. Therefore, a model that achieves lower accuracy on this validation data can still be better than a model with higher accuracy on the old data. And if we look now how the model plays, we do indeed see some obvious changes. Instead of taking no actions at all, it seems to take quite a bit of random actions. But we shouldn't of course forget that only 30 minutes of gameplay went into this so far. So before trying to fix anything, let's play for 2 more hours and see how that affects our model. Let's see if the last 2 pretty painful hours were actually worth it. And indeed we get 5% extra accuracy, so let's directly check how that translates in-game. Unfortunately, it seems the in-game improvements are only small. Since Temple Run is not really the type of game you wanna play for 5 hours straight, I tried to increase our model's accuracy by playing around with the architecture of our neural network, trying different activation functions, different optimizers, and basically just letting my GPU glow. Unfortunately, I just couldn't get above the 80% accuracy line, and I ran out of ideas what I could do. So at some point the last option I could think of was to further increase our training data. So there we go, another exciting 2 hours with the game Temple Run. What's even worse is that this effort didn't even yield any significant improvements. This probably wouldn't be enough to win the roommate challenge against Nick, so I decided to try one last idea. To make a long story short, I now decided to use colored pictures. And in order to not run into our old problem of too much data again, I decreased the size of our images even more. So if this is our original image, now we use images like this. Unfortunately, that also means I need to start from scratch when it comes to gathering training data. Since my motivation of playing another 6 hours of Temple Run was rather low, I decided that I will gather training data for no longer than 2 hours, and that will be it. If this won't lead to any further improvements, I just have to hope that Nick will really suck at this game. Additionally to using color pictures, I made some slight changes to the way actions are detected. So let's hope all these changes weren't for nothing. And indeed, now the model gets a mind-blowing 89% accuracy. Instead of testing this model now by myself, let's just get Nick and start the Battle of Roommates. Dann würde ich sagen, du spielst jetzt 5 bis 10 Mal. Wir schauen, was du so für Scores rausbekommst und dann schauen wir, was mein Programm so macht. Okay, dann zeig mal, was du kannst.
Muss ich da gedrückt halten?
Genau, dann musst du gedrückt halten.
Ah.
Ja. So, dann schauen wir jetzt mal, was die AI so macht. Da kann ich laufen lassen.
Gut.
Nein, da ist er super schlecht drin in diesen roten.
Ah, okay.
Das
Aber sollte ja eigentlich kein Problem sein.
dürfen nicht zu nah aufeinander kommen.
Der ist aber auch angsteinflößend.
Ah, du Depp!
Ah, die kriegt er gar nicht hin.
Ah, den hat er geschafft.
Nur wenn das Ding hinter ihm ist.
Ja. Okay. Ich kann es halt unwahrscheinlich, also einfach manipulieren, dass es unwahrscheinlicher wird, dass er sich entscheidet, nichts zu tun, indem ich einfach den Output-Vektor manipuliere. Also genau die erste Zahl ist, wie wahrscheinlich es ist, dass er nichts macht. Da ziehe ich jetzt einfach ein bisschen was ab. Okay. Ja.
Aber das war's.
Hey, krass.
Echt gut.
Spring, nein! Aber okay.